Hey there, in this video we are talking about arrays and pointer arithmetic in C++, and this covers sections 9.3 and 9.4 in the Gaddis C++ book. So at this point, based on the two prior videos that we've done, we know that pointers store addresses in the memory system. They're just numbers. And on the other hand, dynamic memory is interesting to store really big data structures as arrays. So the point of this lecture is, how do arrays and pointers interact? What is the relationship between them? Okay, so here's the short story, the relationship between arrays and pointers. They are the same thing. There is no difference. You've been using pointers all along as you've been using arrays, and you didn't know it, right? They're the same thing. So we did actually allude to that in the last couple of videos. We kind of pointed that out in our review of arrays video, but here it is again. An array name, all by itself, is actually holding the starting address of an array. So to make that really clear, here's an example. If I make an integer array called vals, and I initialize it to 4, 7, 11, obviously there's three things there. 4 integers are being stored in memory. And if I count out vals with no square brackets, I'm going to see the address of where that array starts in memory. Hypothetically, let's say it starts at address location 4A00, that's an hexadecimal, of course. You would see the 0x4A00 when you printed this out, right? The naked name of the array is actually holding the address of where it starts. Now, when you stick on the square brackets, of course, and you write vals bracket 0, then you would see the 4. You'd see the contents of the first integer in the array. Okay, but that using vals is exactly what happens if you print out a pointer address. And it works in the other direction too. Okay, so if I have an array, like here I've declared an integer array called vals, I could use pointer syntax, right? I could use the dereference operator, and I could write star vals, which is how you dereference a pointer, and you would see the 4, right? You're seeing the contents of the thing that's sitting at the start of the array. Or vice versa, right? So here in the second example, I have declared a pointer, right? I've declared an integer pointer called val pointer. I've set it to the address of vals, because of course vals is actually holding an address. And now, even though I declared that as a pointer, I can stick the brackets onto that and just use that like a normal array, because that it is a normal array. That's exactly what arrays do anyway. So now if I put on val pointer bracket 1, I would see the 7, right? See the thing one step down from the start of the array. Fascinating. Now let's be clear about that, right? We've got those brackets there. Let's think about really clearly about exactly what happens when you stick the brackets onto the end of what's really a pointer, right? When I write vals bracket index, what that tells the C++ compiler is go to that starting address at vals, right? And then go another index steps further down, where when I say step, each step is sized to the size of the data. And then dereference that location. Go look in that location and tell me what's in there. So vals bracket index is effectively the same as this piece of code here. Go to vals, I mean it's a numerical address, add in a certain number of steps, the index times the size of the type, right? So however many steps down you need to go, find that address, and then finally dereference it and tell me what's sitting there. Really, that's what's happening with vals bracket index. Now, if you want to do that in actual C++, and we're going to practice that, the thing that's a little bit easier is that size multiplier is automatically tracked for any pointer. Anytime you're doing pointer arithmetic like that, I got a pointer, I'm adding something to it, C++ compiler will automatically go, the number of steps is obviously sized to the data, so it's going to automatically take care of that. And what we could actually really write in C++ is just star parentheses val plus index. So you go to the vals address, you're adding a certain number of steps, C++ knows what the step size is, and then dereference it and see what's sitting there. Now those parentheses, if you are doing it this way, those parentheses are required because if you look in the precedence list in the appendix at the back of the book, or the order of operations, the dereference asterisk has a very, very high precedence, way up in the order of operations, higher than plus or minus or times or divide. So if you left off the parentheses, what would happen is you would dereference vals, right? You'd get what's at the start of the array, get that number, like maybe 4, and then add index into it, and that's clearly not what you want. So you do need the parentheses here because of the precedence issues. We're going to practice that in some labs, to be clear about that. So here is program 9.7 that gives a demonstration of that happening. And what's happening here is on line 10, they're declaring a double array called coins, right? And initializing it to the value of standard change in America, right? In addition to that, they're declaring a double pointer called double pointer. I mean, that makes sense, right? And we're going to kind of interact with these two things. On line 15, you're setting double pointer to the address of coins, right? So they are now holding the same address, and they're effectively the same thing. On line 19, 20, 21, we're going to print out everything in the array. And if you look in the body of the loop here, what we're doing is we're using array syntax, but we're using array syntax with what was actually declared to be a double pointer, right? So take the double pointer, stick on the square brackets, that totally works, right? You're treating it like an array. On the other hand, down line 25, 26, 27, we're going to print it out all again, but here we're going to use pointer syntax, right? And the interesting thing is that coins wasn't declared as a pointer, it was declared as an array, but that's really the same thing. So you can use that address plus the count of the loop and then dereference it, and that works and actually winds up printing the exact same thing. So two different ways of accessing stuff in an array, and you can actually mix and match. Right? You can take an array name and treat it like a pointer. You can take a pointer name and treat it like it's an array. And either one of those things work. And if you do actually run this, you see the program output actually does print both things the exact same way. So we are certainly accustomed to doing it like line 21 most of the time with the square brackets. I would say that some programmers, if they're doing a whole lot of programming with pointers, they just get in that mental headspace where they are just thinking about pointers and addresses and locations all the time. So if a programmer is doing a lot of that work on a particular day, they're probably going to write what's on line 27 maybe, right? They say, okay, pointer, go here and go another couple steps down and then dereference that. That actually might be what comes out of their fingers on a particular day. But either one is perfectly fine. Okay, so at this point, I feel it's a good time for a little mini quiz on the pointer arithmetic issues that we've been talking about. I have a little code file here that I wrote, and the point here is to quiz my students on what's going to happen. It's got some arrays here. It's got some statements that deal with pointers and dereferencing and stuff like that. So let's step through this and see if you can state what's going to happen from moment to moment with this particular program. Let me compile this. Great, it compiles. So you can see that I'm making an integer array called int array. It's got 3 things in it. I'm making a double array called double array. It's got 3 things with decimals in it. And just for starters, right, when I start running this, what are those lines going to do? Lines 18, 19, 20. Maybe pause the video and just see if you can stay out loud what's going to happen there. Okay, so hopefully you realize that line 18, right, hopefully we agree with this, int array, that's the naked name of the array. You're going to see the address of where the array starts in memory. I don't know where it is, but we'll see the address, and of course it'll be written in hexadecimal, right? Now, the next thing there is that int array bracket 0. I mean, we all know what that does. That actually gets the first thing in the array. So you're going to see the 10 there. And then line 20, okay, so you go to this address int array, you dereference it, so I guess you're going to see the thing sitting at the start of the array. Now you'll also see 10, right? Let's confirm that. Great. Okay, so here's the address of our int array, right? It's at hexadecimal 7AFE14 for what it's worth. And then I've accessed the 10 2 different ways, once with array syntax and once with pointer dereferencing syntax. Okay, so here's where the real quiz starts. When I hit a key, we're now going to go down to line 22, right, where it says count int array plus 1. What do you think is going to get printed out for that? Let's see. Okay, so remember that's pointer arithmetic, right? The adding, the plus, is not on any of the values in the array. It's on the address that int array is holding. Int array, that's the address 7AFE14, and we've added 1 to it, but C++ is automatically keeping track. When I said plus 1, I must mean 1 integer-sized step, and integers are 4 bytes. So what's happened here is it's added 4 to it. Right? It's gone one integer size step further into the memory system, and now I see 7AFE18 having really added 4 bytes to that number. Right? And the size 4 for the data type is automatically handled by C++ as soon as I'm starting to do pointer arithmetic. Let me go a little bit further down here. Okay, so when I hit any key next, it's going to run line 26. What do you think is going to show up from line 26? Okay, so hopefully you realize it's going to be the address, or it's going to be another address of where the double array is in the memory system. So let's see where that is. Okay, so that's an address hexadecimal 7AFDFO. Now, we just discovered something kind of interesting there. Notice that that's a smaller number than the address for the integer array, right? They both match on the 7AF part, and then this D is a lower value than the E in the integer array. So this is actually a smaller number, indicating that the double array is actually put at a lower memory address than integer array. And that's what this compiler does, at least, is when it's creating local variables, it starts off putting the first thing that I declared at the back end of the memory system, at the highest memory address that it had available. And then as I declare more variables, it's actually putting the data further forward at lower addresses every time I make a new local variable. Does C++ have to do that? No, there's no law about that. But that's what this compiler is doing. And so it might be helpful to realize that it's actually putting local variables in memory in backwards order from the high address to the low address. And that's at least what our compiler is doing here today. Okay, so line 28 is about to happen when I press another key. So what do you think we're going to see when it tries to print out double array plus 1? Okay, so for that, you got to realize, again, this is pointer arithmetic. It's going to take that address we're looking at right now, the 7AFDFO, that's the address of double array, add 1 to it, but when C++ sees the plus 1, it's saying one double-sized step, right? This is a double pointer. Doubles are sized 8 bytes on our system. So it's actually going to add 8 bytes worth to this, and we're going to see 7AFDF8, where it just added an 8 on the end where we used to have a 0. Okay, so on line 22, when I added 1 to an integer pointer, it's really adding 4 bytes. But on line 28, when I add 1 to a double pointer, it's actually adding 8 bytes, because the pointer arithmetic is automatically taking the step size according to the data type that you're dealing with. Okay, a couple more details here. Initializing pointers. Again, you don't want garbage data in your pointers, so you can initialize pointers at definition time. Here, in the first example, I'm declaring an integer pointer called numPointer, and I'm immediately handing it the address of where the num variable is. You can do that with the ampersand operator for a single variable. If I have an integer array called val, I can then declare an integer pointer called val pointer, and again immediately initialize it with the address of where val is. You cannot mix pointer data types. So for example, if I have a double variable called cost, right, I can certainly get the address of where cost is, and really that's just a number, right, with ampersand cost. But if I try to assign that into an integer pointer, right, cost is a double. This integer, this PTR is for storing the addresses of integer type stuff. That will not work. C++ will not allow that to compile. Now that makes sense because of the automatic size tracking, right? Integers are data types are a different size than doubles. Integers are 4 bytes for us, doubles are 8. And remember that when you're doing pointer arithmetic, like on the last slide, C++ is automatically tracking the size. So if you could mix and match 4-byte things with 8-byte things, that size tracking would get all corrupted and get confused and wouldn't work. So that's why this is not permitted in C++ to mix pointer data types. That doesn't make any sense. Now, when you do want to test, right, is this pointer legitimate or not, you can probably use that null pointer keyword, hopefully that was initialized one way or the other. So what you might do is write if your pointer equals null pointer, then that's actually not a legitimate pointer, and you should avoid using that. Alternatively, you could write that really, really short. You could write if parentheses exclamation mark PTR. Remember, exclamation mark is the logical not operator. And so if you wanted to get into this error message if the PTR is actually null, right? Remember, null pointer is the 0 address. Let me see. So if pointer was 0, that's false in C++, and not false would turn to true, and you would get into the block and you'd get the error message the exact same way. So I personally tend to write not pointer just because it's super short, but someone else might prefer to write if PTR equals null pointer equals 0 to be very clear on the screen. And maybe that's actually a better idea, honestly. Some other stuff you can do with pointers, pointer arithmetic, like adjusting pointers or comparing pointers. So several different things you can do here. There's an example that makes an array called vals, and then also sets up an integer pointer that starts at the beginning of that array, the same address, right? You can increment or decrement pointers, right? So you can take that pointer, val pointer, you can increment or decrement it, and what that means is it's going to take one data-sized step up, right? So if I have an integer pointer and I do plus plus to it, it's actually going to be adding 4 to it, because you need to go 4 bytes up in order to reach the next integer. But if I did val pointer plus plus, sure enough, it takes one integer-sized step up in the memory system, and now you're looking at the 7. And then if I decrement that, it takes one integer-sized step down, which is really 4 bytes, and now you're back at the beginning of the array, and you're actually looking at the 4. You can add specific numbers, right? If you have a pointer and you need to go a certain number of steps up or down in the memory system, you can add or subtract an integer to it. Again, that's going to be sized to the data type that you're dealing with, actually. So if I now take val pointer, which is currently at the beginning of the array, add 2 to it, C++ reads that as I need to go 2 integers further down the memory system. And then you would be actually looking at the 11. Of course, that's 8 bytes away from where the start of the array was. You can use combined assignment. You can do plus equals or minus equals with integers the same way. It's a little bit shorter to write, possibly. So if I reset val pointer back to the beginning of the array, and I do val pointer plus equals 2, then again, you take 2 steps down the integers, and now you're looking at the 11 again. Finally, you can take 2 pointers and you can subtract them. So what that would do, I have one pointer, I have another pointer, it would tell you how far apart they are. And the result isn't going to be number of bytes, it's going to be number of data steps. So if I take val pointer, which is currently pointing at the 11, the end of the array, and I subtract val, that's actually going to come back with a number 2, right? Telling me that these 2 things are 2 integers apart. Really 8 bytes, but it reports that as 2. So for what it's worth, those are all the things that you can do with pointer arithmetic. It's, C++ is going to keep you safe. Other operators really wouldn't make any sense if you think about it. So you cannot multiply them. You cannot subtract a pointer from a number, or rather, you can't add 2 pointers. That doesn't make any sense. So these are actually all the things you can do with pointers as far as arithmetic goes. All right, so a little bit more example of this is program 9.9 in the book, and a little bit similar to the last one. We're making an integer array called set, okay? We're making an integer pointer called num pointer, and you see that's being initialized to the null pointer keyword, right? So that's a good practice to initialize your pointers to null pointer to make sure there's no garbage data in there. Now, it doesn't make that much difference because when you get down to line 13, you're immediately going to set the address of your array in a num pointer. Right now we're going to deal with that 2 different ways. So here is a loop where we're going to use the pointer to display all the array's contents, right? And I'm going to count whatever the size of the array is, of course. And what's happening is I dereference num pointer, right? And print that out. And the very first time that happens, you see the 5. And then we increment num pointer, and it takes an integer-sized step further into the memory system, and now it's going to be pointing at the 10. So the next time through, you dereference num pointer, and that is actually where the 10's sitting, and you see that. And then you increment it again, takes another integer-sized step down, which is really 4 bytes for what it's worth. And the next time you come through and you dereference that, you see the 15. And obviously that goes all the way through the array. And then down here, we're just going to go backwards is what we're going to do. So by the end of that, you're actually at an address, it's actually just after the 40, as a matter of fact. And now we're going to count the same number of things, get into the body here, decrement the num pointer by one integer size step. That gets you back to the 40. Dereference it, print it out, you're looking at the 40. Come back around, decrement it. Now you've got the address pointing at the 35. And you come all the way back through the array like that. So again, sometimes programmers, if they're in pointer headspace, they might possibly set up a loop like this. I see that happening sometimes for basic string handling functions. Some other kind of like I'm handling an array might possibly use this syntax where you're using pointers instead of square brackets. And this totally works because of the pointer arithmetic working with the plus plus and the minus minus. And remember, it's automatically tracking the correct step size for your data type. If I had a double array and I did this, it would be moving around by 8 bytes at a time. And let me describe some of the problems with pointers that can occur if you misuse them. Granted how powerful pointers are, if something goes wrong, it's actually the most dangerous thing you can possibly do in programming. So in this image here on the top right, obviously the situation that you want is you want your pointer holding a legitimate address to an object, a variable, or an array that's been dynamically allocated. If that linkage gets broken in either direction, you're going to have a major problem. First problem, called a dangling pointer, or some people call this a wild pointer, would be a pointer with an address to an invalid location. And this can result from situations like declaring a pointer but not initializing it. And if you don't initialize it with a legitimate address, you're going to have a random number there, which is what happens with uninitialized data. You're going to have a random address to some location in the memory system that could be any other data or any other variable, frankly. And if you write to a dangling pointer, you're going to be overwriting that other memory, just like when you have a buffer overflow that we talked about back in chapter 7. And you're going to be destroying data. You're going to be overwriting some other variables. Which ones are there? There's no way of predicting. It could be literally anything in your computer system at all. And the result of that is going to be lost data, corrupted data, crashes of your program or other programs, security holes that people could use to take over your computer if it was online, anything like that from a dangling pointer. Really, really, really dangerous like that. Now, if the link is broken in the other direction, you have what's called a memory leak. You have a dynamically allocated object that was legitimately set up, a variable or an array, but you didn't record the address, or the pointer that was meant to hold the address has been lost. And maybe that can result from reassigning the pointer variable. You had a pointer variable that was holding the address of this object, but something happened where that got overwritten with another value. And so if that occurs, this memory here, since there's no pointer recording where it is, now you have no way of deleting the memory from the dynamically allocated system. So that memory is now unusable, can't be used by your program or any other program until the program's either reset or the computer is actually rebooted. So that itself is also a major problem. It might not immediately have a program failure, but if this is part of your system and the program runs for a long time, it's going to be wasting more and more memory like this, and at some point there won't be enough memory to actually do its job anymore. So if you have some kind of really crazy result happening from your program, if the screen's getting corrupted or just really unpredictable lunatic results, I would go in and start looking around your usage of pointers and looking to see if you have maybe a dangling or wild pointer or possibly a memory leak. You really want to avoid these things. They are the most troublesome, hard to track down, problematic danger spots in all of programming. So really try to be careful about your use of pointers. You really don't want to have to deal with either of these issues. So that's a pretty good review of how arrays and pointers interact. And again, the story is they're the same thing. So if you have an array name, you can treat it like a pointer. If you have a pointer, you can treat it like an array with square brackets. Wonderful. And there's also a bunch of techniques for pointer arithmetic possibilities that you might see in particular types of advanced code. So in my class at this point, we would do a lab which is dealing specifically with dynamically allocating big arrays, maybe for the first time. And the other thing that's interesting in this lab, to kind of make it a challenge, is it says use pointer arithmetic to access elements of the array. So at least for this particular lab, in order to practice what we're talking about, you are not permitted to use square brackets for the access. You're required here to use the pointer syntax and get a better understanding about what do the square brackets really do, right? They're taking this address and they're adding a certain number of steps and then they're dereferencing it. That's what they actually do. So that's the point of this lab. Now I will say, okay, so in larger life, right, do not get the idea that you are prohibited from using square brackets for the rest of your life, right? Other than this lab, feel free to keep using square brackets. They're perfectly fine. If you're more comfortable one way or the other, we would accept either one for future assignments. But we do like to practice this at least once. Hopefully it gives you better insight into what the square brackets are really doing for arrays. And then later on, you can do whatever you want. Perfectly fine. So next time, we will have the last lecture for chapter 9. And we know that we're going to be writing modular programs all the time. Our code will be broken up into separate small functions. And so every time we see any kind of new feature or object or data structure, we need to know how to pass it into functions and return it back out of functions. So next time, we're going to be talking about passing and returning pointers into functions and back from functions specifically. And that'll kind of complete the knowledge that we need to use pointers. So I'll see you for that.